just a quick recap were what we did last time. So we started the whole story with the diffusion process. The first approach that we did was to somehow simulate the SDE, right? The stochastic diffusion equation. So we wanted to somehow get the SDE, which takes us from data to noise, and then we wanted to simulate the way backward, right? So we wanted to do that, and then to do this, we just invoked this result on the reverse SDE. But the point was that when we use this, I mean, we can somehow estimate the score up to some accuracy. But at the end of the day, the whole process is not going to exactly do what we want. And the main reason, which we said like it's a bit of, this is still under investigation why this is really happening. But the main reason was that SDE is eventually, the reverse SDE is giving us an approximate of the way we need to move backward, right? And this is not accurate, so we cannot 100% say that if we just go on with that equation, we are really going back to the data. So what we can do instead, we said, OK, maybe we formulate it as a statistical problem, right? So we have a chain rule, which starts from our data and gradually adds noise till it gets to the pure noise, right? And now what we want to do, we want to get back from pure noise gradually to the data again, right? And then we can think of this reverse trajectory to be given by some conditional distribution, and that distribution is something that we want to learn, right? So we started to write down the problem. We said, like, if we start with the noise, and then we gradually move backward, then each time we are making a new sample, which is a noisy version of our original data. And our final purpose is that when we are all the way back in the reverse trajectory at the very end, the distribution that this trajectory is making is going to make the likelihood of data maximum, right? So we wrote down the reverse trajectory distribution. It was a bit messy, but we ended up with such an expression, right? I hope that this is not that far away. Yeah, this is here, right? So this was the final reverse distribution you get in your reverse trajectory, right? Starting from xt, which is sample noise, the latent that you sample, then you start to just do it by reverse chain rule, right? And this chain rule is something that you can learn, right? So this PW here is the one that I will learn. Each time it's going to get the sample that you have and gives you the reverse time sample, right? Now, we wanted to make this distribution a way that when we just compute this whole thing, at the end of the day, we end up with one distribution, PWX0. And that PWX0 is pretty much like our data distribution. So we know this from all we did in the previous chapters. This is a classical maximum likelihood problem. We need to maximize the likelihood of this guy, right? But this guy was, again, a kind of huge integral, so we could not compute this. The idea was that, again, go for variational inference, right? So by variational inference, we basically just do importance sampling. And then when you do the importance sampling, this guy shows up. And then instead of having your log likelihood, we actually now have some expression which is computed by sampling that is easier to compute, right? And then we went on and wrote down the ELBO. So we found this particular ELBO. And that was the thing that we wanted to maximize. So instead of maximizing the likelihood itself, we are going to maximize the ELBO, right? That was the whole idea. Good thing about this problem was that this particular posterior distribution lambda that we have here, we can actually compute it, right? So this is not very complicated. What was the reason that we could compute this? Why I can compute this posterior, so the posterior of every single sample at any time, given the original data that I started noising. The main reason was the Gaussian noise, right? So every single time that we wanted to look at any sample, we did it together. Any sample in time that we have, since we start with x0, And each time we add, when we are noising, we add a bit of Gaussian noise. So if you go on in time, at any particular time xt, you can always write it down as a kind of original data multiplied by some efficient coefficient alpha bar t, right? So that was the data part. And then we had 1 minus alpha bar t, some epsilon t, right? This was the Gaussian noise. So you could, at every single time, you really don't need to know all the things before in time, right? If you know the very beginning, your data sample, then you are able to describe your particular time sample statistically, right? Because you would say it's going to look like my data times a coefficient, which I do know, right? Plus another coefficient times standard Gaussian process, right? So this was the key property of this diffusion process, because this was Gaussian always. Then at every single time, we had also the direct link, right? We talked about the direct link as well. So now, we wanted to maximize this guy. This posterior, we could compute it. And then the last thing we did last time was that we played around with the posterior, and we found out that eventually, for every single time, we need such an expression. And this expression is something easy that we can compute, right? So we ended up having this calculation. The posterior of particular time t minus 1, given what we have at time t and time 0, right? And now if you want to compute this, this was the last thing we did on Tuesday, right? So you just open up in definition. So you would say this is going to be the distribution at time t minus 1 and time t and time 0 divided by time t and time 0. And then we're going to again use chain rule, right? So I'm going to open this guy, condition to x0, and then I multiply to the data distribution. I can simplify the red terms, right? And then it's going to remain only these two guys. Again, I use the property of the chain rule, Markov-chain, and then I write it down in this form. This is the guy that we can compute, right? So when you look at the blue term is asking you the distribution at one particular time, given that you have your data, right? So this is the distribution at any time, like t or t minus 1, given that x0 is given to you, right? And that is something you can easily write down, right? When this is given, then this guy is simply a Gaussian distribution, right? So the blue term is Gaussian. What about the green term? The green term is the distribution at time t, assuming that the previous time sample is given to you. What is that guy? Again, it's a Gaussian, right? Because at particular time t, you can also write it down in terms of the previous time. So you can write it down as square root of alpha t, x t minus 1, plus square root of 1 minus alpha t, some other epsilon tilde t, right? This guy is not this one, of course, but they are the same statistically, right? So distribution-wise, they are both Gaussian, zero mean unit variance, right? And then I can describe this guy in terms of xt minus 1. I can describe this guy in terms of x0. So everything here we have is given, so we can explicitly write down our distribution. Everybody's remembering what we did? Right? OK, cool. Now, if you write down, so this is basically what I wrote on the board. So here what you have is the distribution of xt given the previous time, or xt given your data sample, and both of them are Gaussian. So you can write down those Gaussian distribution in this form, and then you can put it inside that expression that you saw, this fraction here. You just replace into this fraction, you do a bit of math, you end up seeing that this distribution is again a Gaussian distribution with a new mean, a new variance. Right? It's not magic, nothing. Just write down the exponentials, make same denominator for the fractions, and then it gonna pops out. Okay? So this is going to be the posterior distribution. So the distribution of xt minus 1, assuming that, given that, xt and x0 is given to you. So you are now looking at the reverse time. So this means that I have x0, which is my data sample. I start to noise it, so it's going to be x1, then x2. And I keep on going till xt minus 1. And then I make xt out of it. And I keep on going till the end of the time, x capital T. Now, the things that are given to me are this data sample and this guy. And the thing that I'm looking at the distribution is this guy. Okay? So I'm talking about the distribution of this guy. Given that I know what was next in time, right? So you can think of we are now moving backward, right? Reversely. So I am here, so I do know what is xt. I also do know what is x0. The reason, you're going to see it quickly, but you can't imagine, because eventually you are training this model, right? And when you train, you're going to sample one data sample, put it here, you noise it all the way to the end, and now you're moving backward, right? So when you are here, you do know what is this guy, of course, and you do know the sample that you started with, right? So you do know x0 as well. So these guys are given to you. Now you want to talk about the distribution of this guy, right? So, and this guy is going to be a Gaussian distribution. The mean value is a function of x0 and xt, both of them. Okay? So this is the mean value. As you can see here, this expression is just a coefficient. This is, again, a coefficient. Oops, there is a typo here. So this should not be, I guess these are wrong. So this is t minus 1, this is t. So I fixed it in the other section. I forgot to fix it here. So this one, in the second term, the square root of alpha t minus 1, this is alpha t. And alpha bar t is alpha bar t minus 1. Because if this is, in this form currently, the numerator and denominator are going to cancel out, right? It doesn't make sense. Huh? So this is a typo here, this one. OK. Anyways, the point is that I have eta t to be one coefficient computed in terms of alpha that I had, x0. Another coefficient computed again in terms of alpha times xt, right? So you keep it in mind. We're going to make it much easier quickly when we start with DPM, OK? But the key point here is that your mean value is a linear combination of x0 and xt, right? The thing that the noisy version that you see right now and the original data sample, right? So this is a linear combination of them. Again, your variance is computed in terms of alpha t, right? Clear? OK. So this is my Gaussian distribution. Sorry, my posterior distribution, which is Gaussian. And now I'm going to put it inside my ELBO, right? So what I'm going to do, I'm going to replace this lambda with the posterior distribution, right? So if I put this one in this expression, I think we did it last time, but we can do it once again together just to make sure that you get the idea how we are actually propagating through time. So if we consider the trajectory, so if we consider x1 or the original data x0 going to x1 and so on till xt and go on till x capital T, when I want to write down the backward chain rule, how should I open it? So I'm going to start with the distribution of this guy, right? This is the one which I sampled. This is the Gaussian thing I start with when I want to generate, right? So it's going to be p of xt times, the next guy should be exactly xt minus 1 given xt, right? What about the next guy? xt minus 2 given xt minus 1. I don't need xt anymore, right? You remember that, correct? So this is a chain rule, Markov chain. You don't need to write down that guy anymore, right? Because that is same thing going to happen for the posterior, but with this difference that you're going to keep x0 as well, right? So in the posterior case, I'm going to start with xt given x0. That's the one which is corresponding to this term. Then I have a multiplication. It's going to start from t equal by 2. The reason that it starts from t equal by 2, because even if you look at the indices, you are not going to have x0 given x0. This is not going to happen, right? So you don't want to describe the distribution of x0. x0 is given to you, right? So you're going to start from x1 given x2 and x0, x3 given x4 and so on, right? So it's going to start from t equal by 2, but in the denominator you're going to have it from 1 going to t, right? You have it because here you're easily moving backward, xt going xt minus 1, so on until you get here, right? So this is going to be your ELBO. And now if you look at this ELBO, one thing that you see here is that, well, I have this multiplication here. If I drop that t equal by 1 in the denominator, so I take that t equal by 1 and put it somewhere else, right? Then I have multiplication, same multiplication in numerator and denominator, so I can write it down as the multiplication of the fractions, right? So I can write this down as xt divided by p of xt divided by q of xt given x0. So this is the first term, right? You see it? Then I just factor out t equal by 1 in denominator, okay? If I put t equal by 1 in the denominator in that product, you're going to see that here you have x0 given x1, right? So I'm going to take that guy out. Then my product is going to start from 2 to t, right? And then I can write it down as the same term in denominator divided by denominator times, the product from 2 to t, right? So that red term is essentially the case of t equal by 1 in denominator, which I factored it out. Everybody's clear? So nothing is specific, just a simple math, right? Everybody's following? Okay. Now that I have this one, this is a logarithm, right? When the logarithm is applied to this multiplication, it's going to turn into sum, right? So I'm going to just apply logarithm to just make it into sum. So this is going to be sum. The first term is going to be a logarithm of this term, right? P divided by Q, right? So I just reverse the fraction, and then I just keep minus here. Everybody's cool with that? So log of P over Q is going to be minus log of Q over P, right? Again, I have from 2 to t different fractions, all of them P by Q, so I'm going to write it down minus logarithm of Q by P, and then the product is going to change into summation, right? And the last term is again plus logarithm of this term. Everybody's cool? Questions? So everybody's clear what we're doing here? Right? So I tried to just simplify ELBO using my posterior that we could compute. It was a Gaussian distribution. Now, one question. This P here, P of xt, I didn't put any W here. Do you know why? Just to make sure you're following. It's just a Gaussian, right? Just the Gaussian that we start sampling with, right? Then we give this Gaussian to our model, and then we start to denoise, right? OK, cool. Great. So I have this expression. Now, you look at this expectation and tell me if you see anything that you have seen before. I have expectation of a logarithm of the fraction of two distributions, and the expectation is taken with respect to one of the distributions. This is the KL divergence, right? Everybody sees that? So the expectation with respect to Q of log of Q divided by P is the KL divergence between Q and P, right? This was the definition. So let me just apply that expectation and write it down in terms of the KL divergences. Okay? So if I do that, then the first term is going to be the KL divergence between Q and P. And now what I'm going to do, I'm going to write down this Q to be Q0 to T. All right? This should be, this should be capital T. Yeah, again, a typo. So this should be a capital T. So this simply I want to say this is the distribution given time 0 I'm going to time t, right? So just a kind of simplified notation. All of them are Gaussian at the end of the day, right? So this guy, all of the all of Q distributions are Gaussian. Now, if we look at this guy again, this is again KL divergence. Now, the distribution is taking me from 0 and t to the time t minus 1, right? This was again the posterior, right? This is again Gaussian. And this distribution is eventually my model at particular time t, which is looking at xt and giving me xt minus 1. And this last term is just expectation of logarithm of 1 distribution. That's it, right? So I cannot yet do anything on this one. Everybody's cool? Questions? Yeah. Which one? In here? So yes, I mean, the thing that I did here, you just start t from 2, then you're going to have one extra term, right? So you can write it down, the product times that the thing, product starts from 2, so you can write it down, the product t from 2 to t of that term that you have, pw xt minus 1 given xt. And then I keep that extra term as a product outside, right? So I'm going to multiply it with p of this term when t equals by 1, right? Which is going to be x0 given x1, right? No worries. So I just took it out, right? Now you can write it down as a product of a fraction, right? Yeah. So questions? No question?
I just want to confirm one thing.
Yeah.
So like for the last equation,
yes,
the q0 to t is the equivalent to the qxt given x0, right?
Right, exactly. That's the one. I mean, that's a typo. You should write it down capital T.
Okay.
Yeah, but anyways. Okay. Now, one thing here. In this equation that you are looking for, the important thing, I mean, I do know this is too much expression, but the key thing is that you should not lose the main target. So what is given to us here in this particular expression when we are computing ELBO? What is given to us when we are computing ELBO? Which of these x's is given to us? x0, right? x0 is your data sample, is the image that you are starting to just train your model on, right? So this is one sample you got from your data distribution, right? You put it on the diffusion process, it just got noisy, right? You ended up with noise. Now you're moving backward with your model, you're just denoising it, right? And now when you get back all the way down to the time 0, now you are computing likelihood, right? And then you compute this likelihood at the particular point 0. This is why we write it down ELBO for the given 0, right? And your final target is to find the right W, right? Which maximizes this whole term, right? Everybody's cool? So anything else in between, they are going to somehow cancel out, right? They are going inside these expectations, this KL computation, and they're going to disappear. The only thing that remains here is W, which is your model parameter, the weights of your neural network, and x0, which is the sample you started with, right? So you're computing one sample ELBO, right? And you want to maximize it. If you maximize it, this is equivalent to maximizing the likelihood, and then this hopefully gonna train your model. Everybody's cool? Great. Now, if you see this, then eventually what we want to do at the end of the day is that we want to maximize this ELBO, right? I mean, of course, we're not going to do it for one single x0, right? We are going to just take a batch of samples, right? And then compute this ELBO over all of them, average it over the batch, and then we do the maximization, right? But I mean, if you think of a tiny batch of size 1, then you eventually want to maximize this one, right? Either this guy or its expectation, right? Okay, cool. So if I want to maximize this guy, this is equivalent to, look at this one. This guy here, right? If I want to maximize, first of all, I can minimize the minus this guy, right? So I can get rid of this minus, I can get rid of this second minus, and this plus is going to turn into a minus, right? So I want to minimize this guy. Now that I want to minimize this guy, look at this expression here and tell me which guys here depend on W, your model parameter. Last two, right? This guy does not depend on your W, right? This is the Q, the posterior, which you computed out of your noising process, right? And your noising process does not depend on your model, right? You just get one data and you add gradually noise to it, right? So this guy is not important. Nothing of your model is showing up here. So when you want to minimize, this is going to disappear, right? You don't need this. The only thing remains are these two terms, right? Okay, so I eventually want to minimize this guy. So I can say I want to minimize summation of KL divergences from time 2 to t minus this particular expression, right? Logarithm of the exponent of the distribution, right? And once again, what is given to us here when we want to minimize? x0, right? x0 is given to you. You put x0 inside the red term. The other terms, you can simply compute it. I mean, of course, you need x0 to compute that particular q inside the KL, because that is something computed in terms of x0 and xt. But this one is given by that x0. This one is given simply by your model, right? And then you put it there. You just do the computations. When you do the whole computation, then you're going to have one expression here, one expression here. x0 is specified. You have ELBO for that particular point, right? And then you want to maximize it. You want to maximize ELBO or minimize this guy, right? Cool? Okay, great. Now, what I can say this is equivalent again to a empirical risk minimization, right? So I have every single sample x0. Then I want to compute an empirical risk, and then I want to minimize it, right? If you think about a general case where you have a mini batch, then eventually you're going to collect lots of those x0s, and then you compute this particular term for every single of them, and then you minimize the average of them over the batch. So you can think of your loss function to be this guy, right? So this is the loss function which looks at your model, right? The model PW. It looks at your model, and then it takes one sample x0, it puts inside this model, and then it computes the loss, right? And when you want to do the training, if you think in terms of computational models, this is the only thing you need to be able to do the training, right? You have data, you have this loss, you have the model, you take the data, put it inside your model, you compute the loss, you minimize it, right? That's it. This is the recipe for any deep learning problem, right? So this is the risk function that I do have, and or loss function, sorry, that I have computed for one particular sample as 0, and I want to train my model to do this, right? To minimize this one. Okay? Everybody's clear? Okay. Now, if everything in between, anything in between, was quite complicated, you can simply forget about it. Because whatever we did here in this section was to end up with this particular expression. This is the only thing that we need. We need something to just train the model, right? And from now on, everything is back to future, right? Back to the basic computational machine learning, right? You have the loss function. You just take your data, compute this, average it over batch, and minimize it, right? Now, since loss is clear for us, so we do understand how we can do maximum likelihood now, computationally. Now I want to just specify the model, right? And the whole thing about the diffusion, different diffusion models that you might hear, some of them are quite well known, like DPM and DDPM. Some of them are less known, like those things people use in combined kind of models like DAL-E and other things. All of them are using the same approach. all of them are thinking of a diffusion process going forward and backward. Then they write down this expression. This is going to be their loss. And then they just specify one computational model, compute this guy, and then try to minimize it, right? The only thing that you need to do now is to just find out what is your model. What is this PW exactly, right? That's it. So the typical case in the known diffusion models that we have is that we consider a Gaussian model, okay? And it makes sense to you why Gaussian, right? Because when you are noising, you are adding Gaussian noise, right? So it makes sense when you are denoising, you should just subtract Gaussian noise, right? So what they do typically, they typically consider this guy. And don't worry, we're going to write everything down in very crystal clear way, because this is the way where computational things start. Now, if you do this, if you write down this distribution to be of this form, so eventually something like what we did in variational autoencoder, then you can think of your whole Markov-chain to be described with this probabilistic model. There is a mean value which is computed from x, t, and t. So every single time you look at your time and your noisy sample at time t, you give it into a neural network. This is going to give you mu, right? Mu is the mean value of that process. And then you get this mean value of the process. You sample from a Gaussian distribution with the same mean and variance sigma t squared. And then you just do that's your model. Like you get from xt to xt minus 1. Okay? That's it. Okay? Now, if you think about this and you put it here inside the equations, you're going to see that those KL divergences are going to look like this, right? So you look at the second term in between. So now, looking at this term, if I want to minimize this guy with respect to model, what is the term which is going to show up? Only the first term, right? Because this term depends on sigma and rho. Rho is the variance of the posterior. Sigma is the variance of your model. And they are not being trained, right? They are not depending on your model parameters, so you can drop them, right? One other thing again, if you write down that logarithm term, log of p, the last term which was not showing up in any KL, right? If you write down that one, since this is again e to power minus something, it's going to end up being minus the same thing, right? Again, inside this expression, which guy is going to show up in our minimization? Only the first term, right? The second term depends on sigma 1, which is not important, right? Right? So at the end of the day, when you just put these two expressions inside the original term that I showed you, you're going to end up with such a thing. So, meaning that you are looking at every single time, and then you try to make the output of this mean neural network, the neural network that is computing the mean value for you, you try to make that one looking exactly like the corresponding mean in the posterior, right? So your model, the mean value of your model at time 1 should be exactly like, at time 2, say, should be exactly like eta 2. At time 3 should be exactly like eta 3, and so on towards the end. And I have one extra thing here, and that extra thing going to be exactly the same thing. So the output of my model, mu w, at time 1 should be exactly like, instead of eta 1, which I don't have, it should be x0, right? So if I just define eta 1 to be x0, so I'm going to call eta 1 to be x0, then I can simply write it down in this form, right? Now, this form, which is given for a Gaussian model, is a very simple form, right? So as I said, you can forget about whatever we had before, right? What you can say every single time, so I have this process starting from 0 to 1 to t, and at every single time I am able to compute eta t out of it, right? So I can compute eta 1 here, I can compute eta t here, I can compute eta capital T here, right? I can compute all of them. You agree with me, right? You remember eta Oh, okay, maybe I can write it. Just take a bit of board. So eta t, it was something like one coefficient. This was one coefficient depending on t, right? So I'm going to call it ct. This was one coefficient times x0 plus another coefficient. Okay, I'm going to call it, I don't know, bt, something else, times xt, right? Now, when I am doing the training, I have x0, right? Because I am computing my loss at the particular sample x0, right? x0 is given to me, so I can put x0 here, and I can put xt also here, right? Which is the guy on this trajectory, right? And now, at every single time, I am able to compute those eta values, right? So I can say at time t, capital T, I have eta t. At the previous time, I have eta t minus 1. And so on. I keep on going, eta t. And so on, I'm going to have eta 2. And I need eta 1. And I'm going to just define eta 1 to be exactly x0 itself, right? Clear? Now, the thing is that I have these values. These are my labels somehow, right? And every single time I can give this xt into my neural network, which is this neural network mu. And out of this guy and time, I can compute one output, right? So I can also compute out of this one mu of w at time t, right? Out of this one, mu of w at time t minus 1, right? Mu of w at time small t, and so on, right? Now the thing that I want to do, I want to make these two the same, and these two the same, and these two the same, and so on, right? Everybody's clear? So this is the loss that I'm going to have at the end of the day. So I hope that despite all of the calculation, I mean too much of indices and too much of typos at the same time, you got the final idea, right? So the final idea is that when you think about a Gaussian denoising, like every single time you're just doing a Gaussian denoising, this is going exactly through a Gaussian process, then the whole thing that you need to do at the end of the day is that you look at your mean, the neural network which compute the mean value every single time, and you try to make that output exactly looking like your posterior mean, right? And you go backward in time. Everybody's cool? Questions? So if you got no question, now the hard part of the story is over. Okay? Now, looking at this final conclusion, this somehow motivated people to just design what we nowadays know it as DPM, or the more specific one, DDPM, denoising diffusion probabilistic model, which is actually the one probably anyone who talks about diffusion model is thinking about that. The one which estimates the noise. Yeah? You hear people talking about diffusion model. You estimate the noise. And this is the one, right? But you really didn't start with estimating the noise. Okay? I hope that you at least got this idea. You're going to see it quickly in this section. The key point is that you're actually trying to just maximize the likelihood. But it turns out that you can do it efficiently if you just somehow estimate the noise. Okay? So everybody's clear about the target now, right? So from now on, it's OK if when I want to just train my model, I just write down this loss function, right? This is totally fine for you, right? If you find it a bit complicated right now, so OK, forget about all the details. Just take it from my side. This is the right loss function that you can train with. And now this is the only thing you need to know to just understand the rest of things. OK?